The box plot, of course, is based on sample data. If we took another sample, we'd get slightly different box plots, maybe extremely different box plots, depending on the variability. But the box plots are built on samples, not on the population. Of course, our whole idea of statistics, we have statistics and parameters. Statistics are based on the sample. Parameters are what we really want information about. Those are the population values. So if I want to know about the population mean, I don't know the population mean. Let's say if I want to know if the mean income of men is greater than the mean income of women, which would be evidence of discrimination, right? That's a hot topic too. But I don't know what the average salary of all men are, what the mean salary of all men or the mean salary of all women. It would cost a lot of money and take a lot of time, and it may be even impossible because it's a moving bar to figure out what those values are. So what do? I take a sample of men and a sample of women, and I'm dependent on that sample now. So when I take a sample, I get the sample mean, and that is X bar. So X bar estimates the population mean, which is known as mu. And until we know those symbols and are very familiar with those symbols, we can't really provide great inference on anything. We can't get those mixed up. We've got to have it down pat that X bar is the sample and X bar estimates mu. And you might say if X bar men is bigger than X bar women, and I got this in some of the quizzes, oh, well, X bar men is bigger than X bar women, or X bar intrinsic is bigger than X bar extrinsic. So we know that mu intrinsic is bigger than mu extrinsic. Just because X bar 1 is bigger than X bar 2 does not mean that mu 1 is bigger than mu 2. That is the key of what we're going to do. We're going to develop tests to provide evidence or to provide inference and confidence as to which one is bigger, but we're never going to know. We're never going to know unless we take a census. So we're never going to know if mu1 is bigger than mu2. We're only going to be able to have a conclusion with a high level of confidence that since X bar 1 was so much bigger than X bar 2, we're going to conclude that mu1 is bigger than mu2 or not. That's going to be rejecting or failing to reject the null hypothesis. We're going to go over and over and over that. But that is the big idea. X bar 1 and X bar 2 are always going to be a little bit different. Are they significantly different to imply that mu1 is bigger than mu2 or smaller mu2 or whatever we're trying to test? So that's what the mean. Obviously, there's more statistics than the mean. There's also the standard deviation. So from the sample, we can get a measure of variability. That's going to be called S. That's what we refer to as S. And Greek symbols are usually reserved for parameters, for population values, parameters. So the population standard deviation is sigma. S estimates sigma. You're not wasting your time by burning those into your mind if they're not already there, because we're going to be using them again and again and again, and we can't get the bigger concepts if we're still trying to fit those pieces together. You probably already know this, but the standard deviation, you square it, you get the variance. So, of course, this one's S squared and this one's sigma squared. Lots of other symbols out there. Burn those into your mind, especially which ones are the samples and which ones are the population, the parameters. Okay, great. So cause and effect. So there's two big ideas that I want to go over today. One of them is this cause and effect, and the other one is permutation tests. So we're going to just jump right into it. You've already seen the asynchronous material, so I'm just going to review it, ask tons of questions as they come up. We have this creativity, the case study from chapter 1. Basically, this is a snapshot from your book. We had 24 intrinsic values and 23 extrinsic values. I've read everybody's quiz responses for today, or everyone that submitted them by 4 or 5 o'clock today. And I've got some great, answers. One of them on here was, does it matter that the poems may or may not have been randomized to the judges? And I got some great responses on that. And yeah, you could list a lot of reasons why, to make sure that this is truly a randomized experiment, that we'd have to randomize the ordering that the poems are presented to these judges as well. But the big idea here, leaving that aside, the big idea here is a randomized experiment versus an observational study. And the whole difference in those two is whether or not subjects can be randomly assigned to the groups, to the treatment groups, or to the control in the treatment group, in this case, intrinsic and extrinsic. And sure enough, they can, and these were. And you can see it right here. You have this whole subject, so we have this pool of people that are going to be in our study, we flip a coin or some random mechanism, picking numbers out of a hat or letting R pick some random numbers, and then assigning them based on, you get a heads, you go to treatment 1. You go to tails, you go to treatment 2. So heads, 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 tails, and people get randomly assigned to groups that way. That is the way that this was done here. Now, now another piece, and this is what always gets confused in these things, and I want to iron it out here, and I really don't believe unless we ask questions in this kind of environment that we'll all really get it as a team together, is that one is a randomized experiment, and we're going to see that later, and you've already seen it. If we have a randomized experiment, we can infer causality. If we don't, we can only infer an association. Something totally separate than that is whether or not we had a random sample. Of course, the word random, or the root word random, is in both. But a randomized experiment, as everyone wrote in their quiz, a randomized experiment is randomly assigning subjects to groups. The random sample, not a randomized, a random sample has nothing to do with the allocation to the groups. It has to do with how we pulled the sample from the population. How did we get those people to be in the study in the beginning? And if everyone had the same chance of being selected, then it's a random sample. And simply, if everyone did not have the same chance of being selected, then it's not. And you can imagine, I'm on my soapbox here, so I'll keep going, but this is a perfect time to talk about it. If we have a random sample from the population, then we believe that that sample is representative of that population. And if we can believe that that sample is really representative of that population, meaning that the percentage of men in the sample is about the same percentage of the men in the population, we don't know that for sure, but we have no reason to believe that it's not, because we randomly pulled them. Everybody had the same chance of being selected. If we have that, then whatever inference we find about this sample, we can assume that that applies to all the millions of people in the population that came from. That's huge ability of statistics. And it's inference, and we're stretching it, but the idea is that if we have a random sample, we can apply our inference if we find a significant difference to imply that would be that would come from any sample that we pulled from the population. Somebody had their hand raised, I think, and I missed it. Somebody have a question?
Yes, it is Ashwin. A couple of quick questions. When I read the book and answered the quizzes, so I think first thing that came to my mind was, how big the population should be. And let me give you an example, right? So I work for a Fidelity Investment financial services company. We recently are undertaking a project, and we are trying to understand what makes a manager a great manager. So what are the effective characteristics of the manager? We're trying to see if the manager is using the tools that the company builds for them, does it make them effective or not? So in this process, can we say all the managers in our company are the population, and if we randomly select some of the managers from that population, does it mean that we are doing a random sample?
That's right. If every manager, before we get started too fast, we end up with what's called finite population. And when you hit the sampling course, you learn how to make adjustments for this finite population. We usually in this class will assume that we have a population of infinite size, or practically infinite. But yes, in your example, if you have a bunch of managers, that's your population, and you have a mechanism at which every manager has the same chance of being selected into participating in the study, then whatever inference you find, if using these tools finds out to be advantageous, the inference is that would be true for any manager, for any manager in your company.
Gotcha. Thank you.
That's right, and that's a great example. The opposite of that would be, what about, how about in this study, in the study that we have here? These subjects volunteered. And if they volunteered, say they put, I forgot exactly how they volunteered, but let's say that they put a radio announcement out on the radio, and they said, hey, on some rock station. So you're listening to this rock station, and they say, hey, we're doing this study on writing haikus. We'll pay you $10, come on down. And so they get these 47 people. So think about that for a second. If the population is everybody in Dallas and the sample is 47 people that were recruited by listening to The Edge, which is a rock station in Dallas, did everybody have the same chance of being selected? And the answer there is, of course, certainly not. Only people that were listening to rock, that particular rock station at that particular time, really had a chance of being selected, or certainly had a much better chance of being selected into the study than those who did not. And so what you might end up getting is, if you find a significant difference in the intrinsic and extrinsic group, it may just be that intrinsic motivation works for people that are up listening to rock music from 2 to 3 in the afternoon, because that's the sample that you pulled. It doesn't mean that that's true, but there's no safeguards against that being true. So, so the be-all, end-all here, and I spent so much time on this because I really want to drive it home, is random samples are tough. It's really expensive and really hard to get a random sample. When you go around looking at all these political, and that's this is really a non-mathematical idea, right? We go into experimental stats, and we're like, where's all the math? I think the biggest piece of it is what we're talking about right now, is because we can go through and find the fanciest methods, but at the end of the day, when we find a difference, we find a significant difference, who can we apply that to? And is it causal or associative? And is it just for our sample, or does that apply to the millions of people that came from? Those are really important questions that have really important implications. I saw somebody just raise their hand, and I just remember Robert, before whoever just raised their hand asked, did Robert have a question, or did I?
Yeah,
I
did.
Okay.
So my question is, the book made a point that when you're doing these random samples, it's important that the population is well represented in that sample. So what if you take the population, the random sample, and you decide that the population isn't represented well? At what point does it become redundant to keep taking those random samples to make sure that the population is well represented?
So if I understand the question correctly, was we take a random sample so that the sample is representative of the population, and then I think you said what happens, or not what happens, but what if the sample is not representative of the population?
Yeah, like say you take the random sample and you get way more men than women, disproportionately to what you think the population would actually be. At what point are you allowed to actually take samples to get something that you're happy with versus skewing data in what you want it to be?
So these are the gray areas, not really gray areas, but these are the deeper areas of statistics that you want to get into, and that's where it kind of becomes the philosophy. But my first question to you would be, how do we know what the true percentages of men and women are? That's some information that we would definitely want to use when gathering a sample. And if we're gathering it from the United States, of course we have the census, which should give us a pretty good idea of what the percentage of men and women are. And when you take the sample, it happens to be all men. And when you'll hit this a lot when you hit sampling, there's things called stratified sampling and probability sampling where yes, you continue to randomly sample from your population until whatever the stipulations of your sample are met. So it's just more in-depth sampling question. But if you have 60% men and 40% women in the United States, and you take a random sample, you can say you take a random sample of 100. If you want to fix that, if you know that that's the percentages that you want, then you keep randomly sampling until you get close to those percentages, or until or you can randomly sample 60 men and randomly sample 40 women, and you can fix that percentage exactly. Of course, there's other things in the population than just men and women. So at some point, you're not going to match all of those. You're not going to match all of those characteristics, but you can do what's called, again, that's what I just gave you as an example of stratified sampling. And again, you can't fix every characteristic, but I guess that's where you would just have a random sample. If you happen to know those parameters from the population, you can work with those, but a lot of times you don't, in which case you just take a random sample and you're hoping basically, that you've got what is considered what is actually represented in the sample. So I guess that's my best answer to that one without taking a sampling course. But to Robert's point, no sample is perfect and all models are wrong. But certainly we want to have safeguards against things that we would know to be wrong, such as if we want to know the average shoe size, just taking a sample of the basketball team because it was called a convenient sample. That's what would be a convenient sample. Because we know that if we're just sampling from the basketball team, our shoe sizes should be probably biased high, and that's not representative of the sample. So I guess the be-all, end-all is that you want to grab a sample that you don't know is not representative. So if you have the money and the resources, then sure, you can keep sampling as many as you can to try to match those characteristics. Okay, I didn't see who asked that last question, but it popped up and went away. I know there's at least one person in the queue. Maybe start.
Yeah, me. Can you guys hear me okay?
Yeah. Shelton.
All right, cool. So it kind of answered my question, but I guess I'll just follow up with, because all models are wrong, but we try to estimate them the best we can. How deep down that rabbit hole do we need to go? Thinking about well, maybe this sample isn't valid because of this, and this. I found myself doing that with a couple of the quiz questions, a couple of the homework questions, and even this example, in the book, you can always try and think about some type of bias that the guys reading the poems may have, and that may throw off the validity of of the experiment. So I don't know. I mean, do we just kind of need to take everything with a grain of salt and just take the examples and take the questions kind of as is, or do we need to constantly be looking for ways to poke holes in what they're doing, if that makes sense?
It does make sense, and I know what you're talking about. The idea is, let me give a quick example of what I think to summarize it all up is that we never know for sure, right? All models are wrong. We never know for sure. Even if we have a randomized sample, it doesn't mean causality. A great example of that is smoking. Is that smoking has been shown to cause cancer. Yet I can show you, I can produce somebody who's smoked their entire life, is 100 years old, and doesn't have cancer. So that would be immediate evidence of a counterexample of smoking not causing cancer. But or maybe somebody else would come around and say smoking does cause cancer. He just hasn't lived long enough for smoking to cause his cancer. But the point being is that in mathematics, and I come from a math background, that was my undergrad and my graduate degree, my master's degree was in math. I want things to be black and white. And I want to, if you say cause, I want it to be 100%. And in statistics, we just have to get around that idea and be comfortable. You said gray area. It's kind of a gray area. It is, we're not 100% sure of anything, which is kind of unsettling. In statistics, though, we don't know. We have a sample. And is our sample good, to Robert's point? It's as good as we can make it. It's got as many safeguards in it as we can possibly afford. And we're going to use the data that we have going forward with things that we hope are true that we don't know are not true. And if we can be 99% confident, then we're going to report that we are 99% confident. If we have questions about the assumptions or about the sampling mechanism, we're going to give our result, and we're going to put a little asterisk at the end of our report, like we're actually going to do, that says, here is my result, here is my p-value, and here are the problems that I think might exist with the study. Here are the concerns. Here are the cautions. And so beware, and I saw some of this in the quiz write-ups, we can't determine anything. Like the word determine in a conclusion, I can't say you never use it, but I can't think of a good time to use it in statistics to determine that men have higher income than women. We can't determine that. We certainly can't prove anything. So we're not going to use those words. We're going to be 99% confident of something. We're going to show a significant difference at the alpha 0.01 level of significance. That's the gray area and the confidence in the alpha level or the significance level is the shades of gray. Is it almost white or is it almost black? Where is the gray area darker or less dark? Whereas in mathematics, I was really comfortable with, hey, it's either black or white. It's either right or it's wrong. And you got to get comfortable with that in statistics as we're trying to find the most useful model and get the most useful inference. We're never going to find the correct one.
Got it.
So there's that. Somebody else just asked a question.
Hey, Bibin, it's Justin. So just
Yeah.
another question. So to have causality, do we have to have a random sample or not necessarily? That's my first question. And the second one is, just from doing a human subject test, it was with a hospital, I was really limited. I had to, get approval, and I had to do a recruitment email. And so whenever we're doing a recruitment email, essentially I had to solicit for people to volunteer for the study. So it really limited, and this is an observational study, but it limited the ability to, to have a random sample. So I guess kind of going back, I mean, we're almost kind of get limited whenever you have an IRB or human resource within an organization to really get a random sample because you have to do what they tell you to do. But I was just kind of curious on your thoughts on or like an experiment, because I haven't done any experimental stuff. Do you have to truly have a random sample to do that, or does that just kind of add strength to your research?
Great. Awesome question. And, and we're going to get used to these. I like where Shelton came up with this gray area. I almost mentioned it before and I got put on a different topic, but to your point of, I lost my train of thought again. Hang on one second. So you were saying that was my point, is that the political surveys that we look at, those are not random samples. When you're looking at the percentage for Trump and the percentage of Clinton, or if you're looking at, who prefers parquet over butter, or whatever it is, you have to have a sample. To get a random sample, hardly any of these studies that you see are random samples. Because as soon as someone says, I don't want to be in the study, right? As soon as you selected them, but they said, I don't want to be in the study. Well, that could be introducing bias, because maybe for whatever reason they don't want to be in the study is what's really driving the effect that you're looking at. So as soon as someone says they don't want to be in the study and you don't get their response, you no longer have a random sample. So you shouldn't be worried that you don't have a random sample, because hardly any sample is. To the extent, we're doing black and white again, to the extent that you have a random sample is to the extent that you believe that your effect, if you found a significant effect, can be extrapolated to the population as a whole. And if you look at, let me get the textbook real quick, and again, hardly any of them are, but if they're not, that doesn't mean that your study is terrible. In fact, like I said, hardly any sample is. Your results can be very compelling, and if you look on page, you already read this, but if you look on page 4, that is the scope and inference study for the creativity study. That's the scope of inference for the creativity study. I'll read it to you really quick since it's important, and I'll get on to what we're talking about here. But since it was a randomized experiment, one may infer that the difference in creativity scores was caused by the difference in motivational questionnaires, because it was a randomized experiment. Because the subjects were not selected randomly from any population, extending this inference to any other group is speculative, right? And that's just what you'd say. That's the gray area. But I like what they said at the end. This deficiency, however, is minor. The causal conclusion is strong, even if it applies only to the recruited subjects. That's what that's a lot of speculation. And some people, that's why they write this up. And that, people can fire in and write notes to the editors, and people can debate it. What we're looking for is the truth. And unless we're able to take a census, we won't know. But in this case, that's kind of an example of how you'd write something like this up. No, it wasn't a random sample, but the results we found were very conclusive. And there's really no reason to believe that, there's no reason really to believe that this doesn't apply to the rest of the population. But statistically, we can't say that this causes a higher mean score in the population. But it's as it said. I forgot what it said already. What was the word that it used? Hang on.
Hi, this is George.
Is minor. The deficiency is minor. So,
I was just gonna, but like with is it Aswani? I think it's his. He was talking about the managers. Whenever he's recruiting out, if you use a broadcast radio, but if he does something like an email, essentially you're recruiting and getting volunteers because you're using email, correct?
Yes.
Yeah, exactly. Sorry, go ahead, Aswani.
No, that's exactly my question was before too is, by reading this book, I think they make the random sampling look very easier and very pretty, but in reality, I think, they just ask for people and they just respond and say that, yeah, we want to be part of this study.
Yeah, that's right. I mean, like I said, aside from very clean clinical trials, even clinical trials for cancer drugs, I mean, sometimes it's impossible to get a random sample, and very rarely you have to have a sampling frame in which you enumerate everybody in your population, and then you can randomly sample numbers and then go track those people down. And when you track them down and they say they don't want to respond, in order to be a truly random sample, you have to convince them to respond. You have to get them to actually give you an answer. We can think of a lot of examples of where bias could be introduced into there, but to kind of leave it here for now is that very rarely are random samples or samples truly random, and there are different extents of random or not. Certainly a volunteer study is not great, but it's better than just going and sampling the basketball team knowingly. So sometimes a volunteer sample is better than a convenient sample, neither of them being as strong as a random sample. But to answer your last question there, though, Justin, is there's this Foursquare chart that I have on a PowerPoint slide here that I think is so powerful, and I started calling it the Foursquare, and I'll refer to it many times. That is actually on page. Oh man, come on. Hang on one second. Oh, there it is, on page 9. On page 9 is the Foursquare, and you can have any combination of those because they're independent. You can have any type of study. Randomized experiment that comes from a random sample, a randomized experiment that comes from a convenient sample, or non-randomized experiment or observational study from both types of sampling. Because the type of sampling is how you get to this stage right here that I'm pointing to. Right? These people, it's this stage that the random sampling comes into. It's this stage that the randomized experiment or the observational study comes into. Right? Once you have your sample is picked, you can either have an observational study or you could have a randomized experiment. Let me keep going. I'll give you a good example of that here in a second. These are what we're going to find next class, or 95% confidence intervals. You've seen those before. They're in the bridge course and in your intro course. We're really going to get under the hood and find out why those work and when they do and when they don't, when they're reliable, when they're not reliable. But this was an example of an observational study. And given the time here, we want to, there's a couple of things that I want to get through. I don't know that we'll have time for this breakout session, unfortunately, but I'll give you the breakout slides, and you can go through those on your own. So it'll be a good example, and I've got the answers there for you. In fact, they're on these slides. But this is an example of starting salaries, male versus female, where here this is an observational study because the two groups are male and female. And of course, when you sample subjects, you cannot randomly assign them to be male or female like you can to be intrinsic or extrinsic. So sometimes it's impossible to actually have a random sample. I mean, a randomized experiment. In this case, that's one of those cases. We sampled the males and the females. You're familiar with that from the reading. So here are the two types of studies. You can have a creativity study that was a randomized experiment, and we have the salary study, which was an observational study. Notice that either way, these could be from a random sample just as these could be from a random sample. Or these could be from a convenient sample just as these could be from a convenient sample. The key is here, can I randomly, that's a randomized experiment. Notice these guys cannot be, whoops, right here, sorry. These guys cannot be randomized to a particular group. They are, wherever they come in, if they're male, they go to the male, if they're female, they go to the female. So causal inference is what we just discussed. So you saw this in the readings. Is causal inference can be drawn from randomized experiments. Causal inference cannot be drawn from observational studies. The next thing I want to talk about here is confounding, a very, very important topic. I'm going to skip this. You can read this. This is an interesting one, but I got a better example of it here. Is this one. So an example of confounding is this guy right here. Maybe males have more education, more seniority, more age. I think these were found that the males looked like they had higher mean salary. The mean of this salary was bigger than the mean of that salary, of the female salary. So potential confounders could be that these guys have more education than those guys, that they have more seniority than those guys, or it may be, just as an example, that if you looked at their age, that all of these people, all of these individuals are actually older than all of these individuals. And what was really driving higher salaries was not male versus female. It was something we didn't record, which could be older and younger, right? But we didn't record it. So the thing with a randomized experiment is if you were able, imagine for a moment, if you were able to randomize gender, then you would theoretically be mixing up all these olders and youngers. Right? If I just flipped a coin and old is just as likely to end up over here as it is to end up over here, then you would imagine that older and younger would be randomized. So that's kind of what we see here. Why don't I run the risk, or as big a risk, as older group and the younger group, that the older group and the younger group, why can I attribute causation here to being in the intrinsic group and the extrinsic group? And it's because I randomize people to that. So when an old person comes into the study, they're equally likely to be in one of these two groups. And so when I look at the olds and youngs, they should look something like that. And a popular question is, and I think Robert might have this question among others, is, well, what happens? It's not impossible that still all the old people are over here and that the young people are over here. It's not impossible. It could happen. And the smaller the study, the more likely it is to happen, right? It's unlikely to happen when I draw 24 times over here and 23 times over here. And this is the idea behind the permutation study. If I only had 5 over here and 4 over here, it'd be pretty easy to get 5 old people over here and the 4 young people over there. It's not impossible that might happen. Then old and young could be a confounding variable, and even though I had a randomized experiment, I might be missing a confounding variable. And you would be right. There is no magic bullet that says randomized experiment means causality. We can draw a causal inference because we've safeguarded against it, but there's a chance that we could be wrong. And that is just something we have to, if we want to minimize that chance, then we got to take a bigger sample. And we can quantify our uncertainty, but in the end, we're going to be uncertain. And again, we're trying to find the most useful model and report. The bigger the sample size, the less likely that is to happen. In science, the whole idea is repeatability. So we're going to come up with our inference. If somebody else repeats the experiment, they should be able to get similar results. Of course, that costs money, though, and it costs time. So we want to get the best inference we can on the first shot, but certainly we do not know in the end. So I wish I had a silver bullet, but that's just, we're trying to get the best information we can from data. And the data is not perfect, and neither is our method. So that's that. But this is the idea of confounding variables. When we hit multiple regression in the second half of this course, we're going to be able to, again, to Robert's point, if we think that age if age is a possible confounding variable, we're just going to end up recording the age of the subjects and putting that into the model. Or doing that in the next course, we'll end up having two-way ANOVAs. If we think there's a possible confounder and we can get that data, we can put it into our model and account for that specific confounder. Not saying there's not other confounders, but we have safeguards against those, and that's part of the experimental design, which is, again, which we'll get into even deeper in the next course. Right now, we're just kind of getting the ideas and the terms. So why do an observational study? Sometimes causation is not the goal. Sometimes we want to predict. Sometimes randomization isn't ethical, like in a cancer treatment placebo drug. We don't want to just say, hey, we really think this drug's going to work, and we just flip a coin and you either get the drug or you don't. Not an ethical way to do it. A lot of times you do a study in which they get both. Maybe arguable scientifically that confounder is unlikely. You may be in a situation where you're like, if there's no significant, like smoking. If you have a big sample size and if you have a huge sample size in I think that's the example I have here. Yeah, this was an actual study, a 6-month smoking ban in Helena. They said, hey, boom, let's do a 6-month smoking ban, restaurants, outdoors, indoors, everywhere, 6-month smoking ban in Helena. And all of a sudden, in 6 months, there was a 40% reduction in heart attacks. It's unlikely that it was because of some other confounder when that was the exact same time period that they did a 6-month smoking ban, and they've never seen a reduction of 40% in heart attacks. It doesn't mean there's not a confounder, it's just that it's unlikely. May have an incidentally observed data set. This is where we live mostly, or most is where I live, where you inherit the data, where you just have this big data set from the Internet of Things or from some customer database that we have that we're just inherit, that we're given, that we didn't have a chance to help design what information we got. Those are often mostly observational studies. So we really live in an observational study world a lot of the time, and most of the time we live outside of a random sample. Inference to population. So we've covered this. I'm going to get to, oh crap. I need to, those got overwritten there a little bit, but random sample, you've got, in order to get a random sample, you also have to define your population. What is it a random sample from? So if you use the phone numbers, even this example, a randomly selected phone numbers for a survey, that's the classic example, but you're only sampling people that have phones. So, the population here would be a random sample, but a random sample from a population of people with phone numbers. And then even then you could argue that that's not a random sample. Like back to, I think, Shelton's point, is do we need to keep looking for, for little technicalities that make it not a random sample? And my answer to that is, does it make a difference? That's how we're going to look at outliers in the future. Yeah, we can go spend millions of dollars going to look at it if something's an outlier, but if it doesn't make a difference if we leave it in or not, then do we need to really worry about it? And so what I was going to say here in this phone number survey is some people have more than one phone number. And if we're taking a random sample of phone numbers and I have 10 phone numbers and you have one, then I have a better chance of being selected into the survey than you do, automatically making it not a random sample. But is that a concern? Is that likely to happen? And that's for us to judge as statisticians and write it into our report. Is it a minor concern or is it a major concern? I'll cover a simple random sample at a different time because there's one more piece I really want to get into here, but definitely read about that. It's just saying that every subset of size n, so not only individuals have the same chance of being selected, but groups of size 5 or size 10, every group has the same chance of being selected also. And that's an important concept. So, okay, so let's go back. That's the one I wanted to get to. Neither study uses random sampling. Yeah, neither one of these studies used random sampling. These all came from the same bank. These, of course, were volunteers. No inference about the larger population is possible because they're not random samples. Does this mean the results are not compelling? Certainly not. We know that they could be very compelling. And the smaller your p-value is, the more confidence you have in that significant difference. And what you do know about the sample drives how compelling it is. And here answers, was it Justin's question maybe, was you can have any combination of them. And it's on page 9. I encourage you to look at this book, at the book for this plot. This breaks it down. This is the randomization experiment. You can have both. If you're in this column, you can make causal inference. If you're in this column, you can make inference to the population. If you're here, you cannot draw causation, and you can only draw an association. That's the opposite. You can draw only an association, and in this box, you can only draw an association to the sample, the subjects that you sample. Does that make it a workbook experiment? No, it kind of looks like that from this chart, but a lot of studies live there. It's less expensive to make this kind of study, and you may find some really significant evidence for whatever it is you're looking for. So, just statistically speaking, that's the breakdown of it, but all of them are important studies. So this is the breakout. Darn it. I wanted to get there. We had some great questions, though, and I want to show you one more thing before we get out of here. But when you do that, I want you to, kind of go through that. You can read this guy, and then try to figure out, is it a random, which one of those squares are you in, basically is what I'm saying. Can you draw a causal inference? Is it to the population, or is it just to the sample? And you can look at those. I'm going to kind of speed through this because the answer is on the next slide. So, well, okay. So, really look at those. Don't look at that. Don't look at that. Okay. Sorry. So, so great. So that was one of the big pillars. I think it might be the biggest pillar in the whole course. Is the rest of the course, we're going to use this. I'm always going to say, hey, give me a scope of inference. And that is whatever you found, if you found a statistically significant result, given all these methods that we're going to go over, what does that mean? Who does that apply to? Does it imply causation, or could there be a confounder, an association? Is there reason to believe that we've safeguarded against that? So not only is there finding significant, we're going to focus most of our time from here on is saying, is this data suggest a significant difference? But again, at the end, what does that mean in the bigger picture is what's usually important to whoever commissioned you to do that study. Okay, so how can we decide, given a sample, if there is a significant difference to draw a scope of inference for? And this is the big idea. In the creativity study, look at that right there. That is what we want to study. We want to know about mu I versus mu E. And if they are the same, then their difference is 0. We're going to cover that more next time. But that's an important thing to remember, is if two things are the same, their difference is 0. Because mathematically, I can find the distribution of a difference. That's not a number right here, but this is. Mu I equals mu E is an idea. Mu I minus mu E is a number. And if I have a number, I can get a distribution. If I get a distribution, I can start determining how rare things are, aka a p-value. We're going to go over here in a second. Basically, in the creativity study, we observed a difference of 4.11 or 4.14420. Right? And if you want to follow along in the book there, if you look at the average of the 24 intrinsic scores and the average of the 23 extrinsic scores, y bar I, which could be x bar, but y bar I minus y bar E, the difference in sample means was 4.144 in favor of intrinsic because it's positive. It's going to be another big idea, right? So is that big enough, right? I don't know. How variable are those samples? Is 4.144 likely to happen by chance? And I can't underline that enough. All we're going to do in these studies is we're going to say, let's assume that there is no difference. I'm going to get big screen on here for just a second. And I apologize. I'm going to go a little bit over here, but it's such a big topic. And if you ever have to go right at 8, that's fine. And I will announce tomorrow on the wall when my office hours are. There will be an office hour on Sunday. Mine will always be on Sundays. But we'll be obviously before the homework's due. So if you have questions on that, you can get to me. And I'm always available via email. And then NIBRAT will have will more than likely have a office hour on Saturday so you can work on your homework that way too. What I want to ask you is this. Let's say that I've got 4, 2, 10, 12, and 3. Let's say I took a sample, and those are the numbers in the sample. Such a huge idea here. Right? Those are the samples. And I want to label those. Let's say I've got, over here, let's say that I've got 3 men and 2 women. Okay, so I haven't given you much information. I gave you the data, and I gave you the gender of the people, and what I would like you to do is assign what you think. We'll never know. We will never know. But I want you to give me the most likely matchings of the genders to the scores. And I'm going to give you this. I'm going to tell you, I'm telling you that the men have a mean score of 5 and a standard deviation of 1. And I'm going to tell you that the women have a mean score of 11 with a standard deviation of 1, say. Now, if I gave you that information, I said, hey, you can expect, it's not impossible to draw a guy that is 11, right? It's just really unlikely because the height of that distribution curve is very small. It's not impossible to draw a woman that got a score of 4 or 5. It's just really unlikely because that area is probability and there's not much area there. So it's not impossible, but given this, hopefully you've come up with what you think the most likely one is. This 4, do you think it's most likely, given this information, a man or a woman? And there's a lot of people here. You can ring it in on the chat if you want to participate with it, or you can just think of it in your head. But 4 is more likely to come from here than it is to come from here. So I would label him or that person male. I would label this a male because 2 isn't likely over here, but it's much more likely than it is to be a woman. 10, that looks like a female. 12, that looks like a female. And 3, that looks like a male. I don't know that those are right, but that's the most useful model I can come up with given the information that I have. That is in large part what we're doing, except how do we make these decisions, and we can quantify it if we're given, or we can assume these distributions. Okay, great. So what I'm going to do, though, next is I'm going to ask you this. Get ready. Let's say that I do this, because that's what I want to know. I don't know these distributions. In the end, I want to test to see if one is bigger than the other one. So let's assume that mu m is equal to mu w. Let's assume that, which means this. That's the men, and that's the women. And I'm just going to make one up here. Let's just say that they're 8 or something like that. So let's assume that. And if we assume that, do you agree that if we assume that now it makes this really hard? What do you think 4 is? If I assume this, do we have any idea of what 4 is? And we don't. It's just as likely, if it's the same distribution, this is just as likely to be a man as it is to be a woman. And so all I can do, and that goes for true for all of these. So M, W, W, M, M. W, W, M, M, M. M, M, W, M, W. All of those assignments are equally as likely as any other one under this assumption. That's a very, very powerful idea, and it's what you read about when you looked at permutation tests. Okay, so let me give you this last little piece here, because it's so fundamental to everything that we're going to study. From here on is what we're going to do is we're going to assume that they're the same. In fact, I'm going to give you this terminology here. We're going to assume the null hypothesis that mu m equals mu w. The alternative hypothesis is, let's say we want to test if mu m is, say, less than mu w. Right? I'm going to go ahead and erase this. Right? if I was to draw it, that's what I'm drawing. I'm saying, hey, under the null, I think they're the same. Under the alternative, I'm going to test to see if there's evidence. I'll never know. But I want to see if there's evidence that this is it. So what I do is I go out and I grab an X bar M and I grab an X bar W. X bar W here. So let's get rid of this. Let's say X bar W turns out to be 10 and X bar M turns out to be 2. Well, X bar W is bigger than X bar M. That is somewhat evidence for HA. But could that be due to random chance? What is the probability that if they were equal that we would see a difference this big? Because X bar M, or this small, X bar M minus X bar W is equal to -8. So our question is simply, if they were equal, what's the probability I would see a difference that big? Right? I'm going to give you a different separate. Let's say that X bar M was, 4 let's say X bar M was 8.1 and X bar W was 8.2. Well, X bar W is bigger than X bar M, but it's only 0.1 bigger. So that's not as much evidence as it is here. Of course, that depends on the variability in your sample. We're going to cover all of that. But for now, just say, hey, variability being the same, that's a bigger difference than that is, right? Sorry, X bar M minus X bar W is equal to -0.1 now. This could just happen to, I took another sample, maybe they switched. That's not a very big difference to make up if they were the same. This is certainly evidence, more evidence, that this one is bigger because it's a negative big number. That's what we want to do. Could this happen if they were equal? Sure, just unlikely. Could this happen if they were equal? Yeah, that might happen all the time, something that extreme or more. That's what a p-value is. So I'm just going to introduce this, and we're going to come back to this topic a ton. I just want you to work with it and read the textbook on this section. And the more you read it, the more it'll get into your mind. What I want to do is show you this code. And I'm really working on, Again, if you got to go, I totally get it, but I think we're really going to make some good progress here. And I got about 10 minutes, I think. I hate to say it. Probably 10 minutes, which could be added fun. But I made this one earlier, and you guys are in an R class. This is the first semester I've really done anything with R in this class. But I'm going to go ahead and go into, you can see this example. This is an example that I put out on the internet, so you can run it in an R window. It'll help you with your R skills. But since we were dealing with the creativity data, I'm going to go ahead and look at the and do the creativity data. So here it is. So what we're going to do with this creativity data is I read in the creativity. So that's just me reading in creativity data from R. And again, it's not trivial on how to use R to get that in there. You can use this though. You just got to get your path right. So creativity. Creativity. So there it is. There's the data. There's the extrinsic, and there's the intrinsic. Extrinsic, intrinsic. Great. So what I'm going to do next is I'm going to look at, I'll just go ahead and run this. You're going to see this eventually. We'll get there. This is a t-test. The only reason I'm running a t-test here is to look at the difference in the means. So there's a mean for the intrinsic and there's a mean for the extrinsic. We know that that difference is 4.144 something. But I'm going to go ahead and run this. And sure enough, the difference, they don't give us the difference here, but here, if we subtract these two numbers, if we do 19.88 minus 15.73, you'll get about 4.144. Hopefully everybody sees that. That's the intrinsic mean. That's the extrinsic mean. Is that difference big enough? So what are we going to do? Hopefully you can see me on there, on the video. How are we going to do this? What we're going to do is we're going to assume that they're equal and then see how often we would see a difference this extreme, 4.144. We're going to assume they're equal, which means what can we do if we assume they're equal? We are going to scramble these labels these labels here, we're going to scramble the labels. So this 5.0, I'm just going to flip a coin. I'm going to make it an intrinsic or an extrinsic. I'm going to make sure that there's 23 of one and 24 of the other one. But this 54, if I assume that there's no difference for intrinsic and extrinsic, then I'm going to label that. And these are the labels that I observed, and I got a difference of 4.144. I'm going to scramble them and see what that difference is and means then. And I'm going to scramble them again, I'm going to scramble them again, and I'm going to scramble them again and again and again. Let me show you what that does. That's what this is here. So 4 IN to number of permutations. I'm going to end up doing this 10,000 times. I'm going to scramble them. That's just scrambling the labels. And then I'm going to look at extrinsic. I'm going to get the, well, you can kind of see where this goes, but I'm going to say, hey, I'm going to scramble them. I'm going to say the first 23, since I scrambled them randomly, I'm going to say the first 23 are extrinsic, and the last 24 are intrinsic, just based on their order. Because I scrambled them, I'll just say, oh, the first 23 are extrinsic, last 23 are intrinsic. I'm going to look at their difference, so the mean of the intrinsic minus the mean of the extrinsic, and I'm going to remember it. So that at the end of the day, I've got 10,000 differences, all assuming that that there was no difference in these distributions, that the mean of the intrinsic was the same as the mean of the extrinsic. And then I'm simply going to say, of those 10,000, how many were bigger than 4.144? Of those 10,000, how many were bigger than 4.144? And so that's what I'm going to run here. So I run it. I'm going to run that guy. And what we end up seeing here, oops, sorry, I was messing around with it earlier. So you're going to look at the X bar holder. What we're going to end up seeing is this. Oh, it's so beautiful. That is the distribution of those 10,000 differences. It's a normal looking distribution. And in theory, we can prove that the difference in means is asymptotically normal. Well, we can essentially, if our sample size is big enough, the distribution of the difference of means has a normal distribution. If we know the distribution, then we can find probabilities. But all we're going to do here is we're going to say, oh, okay, well, we know that the difference is 4.144. That's right about here, right? 4.144, if you can see my cursor. Well, we observed some bigger than that. And in fact, I can tell you we observed, because of our p-value here, notice how we got the p-value. This counter said is if the ones that we observed were bigger than, if the ones that we randomly permuted, of those 10,000 means that I looked at, how many of them are bigger than the ones that I observed in the actual data set? How many of them are bigger than 4.144? That gets put into counter. Every time it happens, I increase counter by 1. And remember, I did that 10,000 times. This is saying 26 out of 10,000, that 0.0026, 26 out of 10,000 works. So I do 26 divided by 10,000, and that gives me the probability. It's not impossible that it can happen, but you would, if they were equal, very rarely by random chance would you see something as extreme as a 4.144, meaning that that is very strong evidence that they actually are not equal, that the intrinsic mean is bigger than the extrinsic mean. And you can see if I run a permutation test, let's say I do it again. Watch what happens to this distribution, right? If I run it, let's just keep running it. If I run it again, changes a little bit. If I run it again, oops. If I run it again, changes a little bit, right? Because it's different permutations. But look what happens to that p-value, right? This time it was 26 out of 10,000. But that's so small. If they were equal, it's just like saying you're going to win the lottery. Let's say I win the lottery 10 times in a row. Do you think I'm cheating? If you assume that I'm not cheating, just like if you assume that these two are equal, if you assume that I'm not cheating, the probability that I would win the lottery 10 times in a row is very small. So what do? You say, well, the probability is very small if you were not cheating, so I'm going to assume the evidence suggests that you are cheating. We can't prove that I'm not cheating or that I am or I'm not cheating, but the evidence suggests that I am cheating if I win 10 times in a row because of what we're seeing here. Because if I assume that I'm not cheating, the evidence is saying that would happen very rarely, and I'm going to assume then that I am cheating. Here, I'm saying, well, let's assume they're equal. If they are equal, the probability we would see a difference in means this big, 4.144, is very small. So I'm going to assume my assumption is wrong. I'm going to conclude that my assumption is wrong, that they're actually not equal, that intrinsic mean is bigger than the extrinsic mean. So hopefully I'll see everybody at office hours on Sunday. I will announce when those are tomorrow. I'll make them. I guess I've got a thing this weekend. I've got kind of a date night thing that my wife bought me for Christmas. But usually they'll be in the afternoon. They'll probably be in the morning on Sunday. I think it'll be very useful. We'll record it. So if you can't see it, but it should help you with your homework, but so should those videos. I can't get out of this thing. Let me show you this one last thing before we break out. Very fun thing we do here at the end. But there is some SAS code, but that's what the video is about. There is SAS code out there that I've given you that will do the exact same thing that I did in R, and please watch those videos. It is going to be confusing at first, but work through it as much as you can, and then ask each other, try to figure it out, and then ask me, and we will work through it, and we will be much stronger for it. I'm just kind of warning you, it's not going to be real easy at the beginning, probably. Let me show you this. You need to read through that, but okay, here's what we just looked at. So this is one from the book. They did it 1,000 times, and they found that more as extreme or more extreme. So they looked at things that were bigger than 4.14 or smaller than negative 4.14. Only 8 out of 1,000 did it. So that p-value is 0.008. That's strong evidence against the null hypothesis. It's saying only 8. If you assume they're equal, only 8 out of 1,000 had something as extreme or more extreme. So I can't prove anything, but the evidence certainly suggests that they're not equal. So how do I do that in SAS? It's going to look like this. So I've got the SAS code out there. I'll let you look at it. And again, I have those videos. I really want to take us through it, but I know time's short, and I already have the videos out there. This is your null hypothesis. This is what it's going to do. That's your null hypothesis. Remember, that's the difference. If the difference is 0, that's assuming equality. And this one is assuming, this is another one we can have of not equal to. And we have a p-value of what it's going to do. What SAS is going to do is it's going to scramble. It's going to use a matrix, but that's black box to us. It's going to make a matrix of 1,000 columns. It's going to scramble those labels under the null hypothesis that they're equal, and then they're going to look at the difference in means for each one and see how many times it was bigger than the one we observed. In this case, it was only bigger 5 out of 1,000 times, so my p-value is 5 divided by 1,000 or 0.005. The code is actually, I've written a code to actually output the lines that were more extreme. You can see this one is more extreme, barely, but more extreme. This one's more extreme, that one's more extreme, that one's more extreme, and that one's more extreme. All the other ones were pretty close to 0. You can see it, right? Most of them are in this area. But every once in a while, by random chance, you're going to happen to get some of the bigger scores in the intrinsic, just at random, and some of the smaller scores in the extrinsic, and you're going to get this big difference. But the observed one of 4.144 is very extreme under the null hypothesis that they're equal. So I'm going to end up with this conclusion. And this is one we're going to get, and I'm going to end it with this. But this is, you're going to get really good at writing these conclusions. You've done great today. Let's just end it on this big bang here. There is strong evidence to suggest that the mean score, I'm not talking about individual scores here, that the mean score of those who received intrinsic motivation is greater than those who received the extrinsic motivation. Since this was a randomized experiment, we can conclude that the intrinsic motivation caused this increase. In addition, since there were volunteers, this is the scope of inference part. Since scope of inference, since there were volunteers, the inference can only be assumed to apply to those 47 subjects, although, as it said in there, that it was a minor infraction, they thought. But although the findings are very intriguing. Why are they intriguing? Because that p-value is so small. And then we get into big data, we're going to see some other issues that's going to kind of mitigate that. But with a small sample size, that's a super small p-value. man, we're going to learn a lot this semester, and this is the foundation. So, so go ahead and get started on that homework. Really work hard together on that code, or separate or together, or separate and then together. And then I'll see you guys. I'll put the time for my office hour out on Sunday. It'll be sometime Sunday morning. So in the end, I can't tell you how much. I mean, I guess I can because you already know. We covered a lot tonight, a lot of very important topics. I'm glad we had some great questions. Look over those PowerPoint slides. They're already in Canvas. And we are going to have, if I ever get my camera back, can anybody see me on my camera, or is it blacked out? Bad timing.
Yeah, it's blacked out.
It's blacked out. All right, this is not good because we got one more thing to do before we get out of here. I'm going to stop it and then start it. Oh, man. Why?
Same thing happened to me. My camera is also blacked out, like I cannot start my camera again.
Yeah, let me go.
This is Hari.
This is not fortunate for me. So we do one thing at the end. So great work today. It's been awesome. Shoot, we do one more thing as a breakout because celebrate everything that we do here at the end. But I don't know. Let me try this thing. If we go over here.